right, let's start the lecture. And just a recap of what we were talking about last time. We introduced Gaussian random variables, which were continuous random variables, so variables where we did have some kind of a density function such that the probability of this real valued random variable can be obtained just by integrating this density function on an interval if you're interested in the probability of it being in an interval. And we saw that we can define a Gaussian random variable, a standard Gaussian or a standard normal random variable with the density function of this form, which is basically e to the minus x squared divided by 2 up to certain normalization so that it degrades to 1. And more generally, when you have a Gaussian random variable with mean mu and variance sigma square, we can write a density function, which is basically a slight change of variable in the first expression. I also claimed, though did not prove, that if you have two independent Gaussian random variables, then basically linear and affine combinations also give you Gaussian variables. So if you multiply a sort of Gaussian by a constant or shift it by a fixed additive constant, then you still get a Gaussian with appropriate mean and variance depending on how you shifted it. And more interestingly, the linear combination of two independent Gaussian random variables is also a Gaussian, and such that the variances add. I mean, we already know that the variances will add. We know that variances add even for pairwise independent random variables. So in particular, x1 and x2, if they are independent, they are pairwise independent. But the interesting part is that it's not just that variance add, we get a Gaussian with the new variance. And we sort of saw how to compute few simple expectations. So we saw that expectations of any odd function of x is 0, just because x is symmetric about the origin. Expectation of x squared was 1, which is the variance for standard normal distribution or standard Gaussian. And I said expectation of x to the 4, and more generally for other kinds of moments, you can find based on one of the problems in the homework. Did anyone figure out what the expectation of x to the 4 is?
Is it 1?
Where do you say that?
I'm just matching the pattern because the exponent is even.
Okay, well, it's no, I mean, there is a pattern, but it's a little more involved. But you can check, and in particular in the homework, we have that if you have G1, G2, G3, G4, which are jointly Gaussian, then the expectation can be written in terms of expectations of pairs. So expectation of G1, G2, expectation of G3, G4, and then similarly expectation of G1, G3, expectation of G2, G4, and one more term which will have, let's say, G1, G4 and G2, G3. And if you take all 4 of them to be equal to x, which are all Gaussian random variables because they're all the same Gaussian random variable, and they are still jointly Gaussian because any linear combination of these 4 is just a linear multiple of x. Then what you get is the expectation of x to the 4 is 3 times expectation of x squared. Expectation of x squared is 1, and so this is 3. And there is a more interesting pattern for higher moments that you can find based on the homework problem. So try to look at it. We also computed the expectation of some function of this form, which we'll need today. So I kind of used it as an example last time. The expectation of e to the lambda x squared we saw is this expression, which is, which makes sense for lambda less than half. And we saw that the expectation is infinite when lambda is greater than half. Okay. Any questions before we continue? Okay. So I'll spend a little bit of time giving a sketch of the proof for this property about linear combinations of Gaussian, of independent Gaussians. It's an important thing to know, and it may not do the entire proof, but I'll at least give you the steps. Okay, so let's start with the second property, which is if you have a Gaussian, you scale it by C1, let's say, and shift it by mu, you get another Gaussian with mean mu and variance C1 squared. Okay. And this, as we kind of said last time, is basically just a little bit a change of variable, and we can sort of do this formally. So we want to, let's say, let's call this random variable z, which is just C1 x1 plus mu. And let's assume that C1 is greater than 0, although as you'll see, it doesn't really matter. And the same argument will also work when C1 is negative. When it's equal to 0, things are less interesting because then we just have mu, which is a fixed constant. And the variance of our Gaussian will be C1 square, which will be 0. So it's a less interesting case. Okay, so let's say C1 is greater than 0. And to understand what this random variable z is, we'll just understand the probability that z is less than equal to t. And as we saw, the density function is nothing but the derivative of this as a function of t. And or if you can write this probability as an integral of some function, then we integral from 0 to t, then that function is the density function of our random variable. Okay, so if we want to compute this probability, just the probability that z is less than equal to t is equal to the probability that x1 is less than equal to t minus mu divided by c1, which is just obtained by manipulating things on both sides of the inequality. X1 is a standard Gaussian, so we know its density function, and so we can calculate what is the probability that x1 is less than equal to something. And here is that expression. And now we want to write it as an integral from minus infinity to t of something. Okay. So we want to write it as integral of some function from minus infinity to t. And whatever that function is will be the density function of our random variable capital Z. That's how we define the density function, really. That if you can write down the probability that the random variable is less than equal to t as some integral from minus infinity to t, then whatever is the function you are integrating is the density function. Okay. This has to be true for all t, by the way. It's not for a specific t, but we should be able to do this for any t. And so all we need to really do is just change the limit in the integral, and that can be achieved by a change of variables. So let's say, let's substitute z is equal to c1 times x plus mu in the integral, and just this change of variable. So the integral now goes from minus infinity to t. If we write the integral over z, x is just C minus mu divided by 2C1 square. And dx is replaced by dz divided by root 2 pi C1. And so this is the density function of our random variable z. And if you look at it, this is exactly the density function of a Gaussian random variable with mean mu and variance C1 square. And we said for a continuous random variable, once we know its density function, we know everything about it. We can calculate for every valid event in the Borel sigma algebra, which is generated by intervals, the probability that the random variable lies inside this interval. So, and we just proved that the density of z is the same as of a random variable which is distributed according to mean mu and variance C1 square. So z is a Gaussian random variable with means mu and variance C1 square. Okay. Any questions before we proceed? A Gaussian is defined by its density. So we were studying some random variable which was obtained by kind of scaling a Gaussian and shifting it. And we computed the density of this new random variable, which also was the density of an appropriate Gaussian. Okay. Going further, we now want to look at, let's say, a linear combination of two Gaussian random variables. And again, we sort of assumed C was positive. If C is negative, nothing much would happen. You will kind of flip one of the inequalities, but then you will also get a negative sign when you do the variable substitution, and you will end up with the same kind of density function. So it doesn't change the proof a lot when C is negative, but you just have to be careful when you're using this inequality. And so that's why I initially only studied the case when C is positive. Okay. And going to the case of two random variables, let's just first study what happens to the variable x plus y if you have x and y which are independent. So right now, I'm not assuming they are Gaussians or anything, but just independent random variables. And if I have x plus y, which is which I'll call a random variable z, then again, I can kind of calculate the density of this random variable by trying to compute the probability that x plus y is less than or equal to t. And I can think of basically, suppose this random variable takes the value little z, then x plus y are adding up to little z. And so x is some number, let's say between minus infinity and infinity, and y is z minus x, so that the sum is equal to z. Z is ranging from minus infinity to t because I'm interested in all values between minus infinity and t. And so this is the probability that the random variable z, which happens to be equal to x plus y, is less than or equal to t. And so whatever appears inside this integral is the density of this random variable z. And so what I just did was computed in terms of the densities of x and y. Let's say f and g is what we're calling the densities of x and y. I computed an expression for the density of z in terms of the densities of x and y. And now we just apply it to the random variables that we are interested in. So let's say we have a standard Gaussian x1, a standard Gaussian x2. And now we are interested in the linear combination c1 x1 plus c2 x2. So let's call this x, let's call this y. And from what we just did on the previous slide, we know that the density of x is whatever is the density of a Gaussian with mean 0 and variance c1 square. This is whatever is the density of a Gaussian with mean 0 and variance c2 square. So this is really f of x. This is really g of c minus x. And so this is the density of c1 x1 plus c2 x2. It's some integral, and you need a little bit of manipulation to show that this is equal to e to the minus z square by c1 square plus c2 square. Sorry. And this I'll ask you to do as an exercise. It's again completing the square in the exponent, and then using the fact that we know how to sort of calculate the integral of e to the minus x square divided by 2, or some scaling of x by a little bit of change of variable. And it's the same integral that we computed last time. E to the minus x square over 2 integrates to square root of 2 pi, and you can compute integrals of appropriately scaled version by change of variable. So it's again a similar computation, but you can use it to show that the above integral is equal to this number, which depends only on z, and you've integrated over x. And once you get that, this is nothing but the density function of a Gaussian with mean 0 and a variance c1 square plus c2 square. So if the density function is equal to that of a Gaussian, this random variable is that Gaussian. Okay. Any questions? And once we have these two properties, the one about scaled Gaussian and also what happens when you add two of them, you can show that by induction, you can also prove that if you take a linear combination of more than two Gaussians, you still get the same kind of behavior. So let's say you have x1, x2, xn, which are all standard Gaussians and independent. Then if you take a linear combination of these, c1, x1, cn, xn, then this is Gaussian with mean 0 and variance, which is summation ci square. Okay. And more interestingly, we can think of it as mean 0 and norm of c square, where c is a vector with coordinates C1 to Cn. So norm of C square is just a shorthand for summation Ci square if you're just thinking of it as in n-dimensional real space under the standard inner product. This particular property is quite useful, and one can think of Hilbert spaces associated with Gaussians. And we'll just use this property in a very simple way in what we do next, but it's useful to just check that you can prove this by induction on the two things we at least sketched the proofs of so far. Any questions before we continue? Okay, so let's do one interesting application of Gaussian random variables. And Gaussians are convenient for this application. They're not necessarily the only kind of random variable with which you can do this, but yeah, and I'll say more about that later. But this is a somewhat surprising result called the Johnson-Lindenstrauss lemma, which can be viewed as a way of kind of reducing the dimension of a data set. So we also saw this problem earlier when we were trying to reduce the dimension of a set of points using singular value decomposition, linear algebra, etc. And we'll compare this approach to the one we had there in a bit. But let's first see the statement of the result. So let's say you have P, which is a set of points in D dimensions. And let's say there are n points in our set. Okay? So the cardinality of P is n. And suppose they're given some parameter epsilon, which is positive, and also, I mean, we're going to think of epsilon as between 0 and 1. In fact, just think of epsilon as a really small positive number. And what we want to do is map or sort of embed our points or sort of map our data set to points in k-dimensional space, where we are going to think of k as so we want the dimension to be much less than what we started with. And by the same time, we want the distances in our data set not to change too much. So distances is one property which we have chosen to care about in this scenario. I mean, of course, maybe you are interested in some other property of the data set, and then we'll have to reason about it accordingly. But a lot of the time, when we think of a data set, we want to think of whether 2 points are close to each other or far apart, as maybe some notion of whether they are similar or not. And here we're just trying to look at the L2 distance. So just the distance according to given by the inner product on R to the D, and which is the standard Euclidean distance that we are used to. And what we want is that we want to map our points to k-dimensional space, but in such a way that if I look at the image of U and image of V, then the distance between these is more or less the same as the distance between U and V. And importantly, we want this for all points in our data set. And what Johnson-Lindenstrauss lemma says, in fact, it says something even stronger, is that you can do this by a simple linear transformation. So there is a linear map which maps points in Rd to R to the K. So it's just a matrix. It's a matrix. If we think of points in R to the D as column vectors with D entries, this is just a matrix with K rows and D columns. And such that when you multiply every point by this matrix, you get new points in a smaller dimensional space. and the distances between any 2 points are roughly the same. Is the statement okay? And an important part of the statement is you can always choose the dimension to be something. Yeah, don't worry too much about the precise form of this expression. Most of the time, we just need an approximate version. But you can always choose the dimension to be something which is logarithmic in the number of points and has a dependence on epsilon as 1 over epsilon squared, roughly. If epsilon is small, epsilon cube term is really negligible. And so, even otherwise, you can just think of this as epsilon square up to a change in the constant above. So roughly log n over epsilon square dimensions are sufficient for a data set with n points. Doesn't matter what was the original dimension of this data set. They could be living in d dimensions. In general, you can show that to realize any kind of distances, it's sufficient to take d to be roughly n. But here you're saying that if you just want this to preserve distances approximately, you can take the dimension to be log n, which is a tremendous saving for many applications. Any questions before we continue? Okay, so let me sort of say what this linear transformation is going to be. We're just going to pick it at random. Like a lot of things in applications of probability, we pick some object at random and then show that this is a good object in the sense it satisfies with high probability all the properties we want it to satisfy. So here, we're just going to pick this linear transformation or equivalently a matrix at random. And this matrix basically is just a matrix where every entry is just a standard Gaussian. Okay. Except for convenience, we'll use a scaling just to sort of just so that we can keep entries to be just standard Gaussians, and then you'll see why the scaling is necessary in a minute. But think of G as a matrix which every entry is just a standard Gaussian. Okay. So this matrix itself is a random matrix, and the linear transformation will just be given by a matrix which is 1 over root k times G. All entries
really
of this
quickly.
Matrix. Yeah.
Sorry. So does this mean that it's a matrix of Gaussians or a matrix of values sampled from a Gaussian?
It's a matrix of Gaussians. So every entry is an independent Gaussian random variable. Okay.
Okay.
So G, yeah, I mean, in some sense, it's not clear what we mean by values sampled from a Gaussian, because if you are sampling 2 values, then you are thinking of these 2 values are both random outcomes. And so you are thinking of basically 2 random variables. And when you are saying that they are sampled from a Gaussian, what you are really saying maybe is that they are sampled from Gaussian distributions with similar parameters, with the same parameters. So same mean and same variance possibly. But if you're saying that they are sampled independently, then they are still independent Gaussian random variables as functions on the probability space. And so that's what we are thinking about in terms of G. So every single entry is an independent random variable. And we have D columns, K rows. So D times K independent Gaussian random variables, each contributing 1 entry of this matrix. Is that okay?
Yeah, that's perfect. Thank you.
Okay. All right. So that's a linear transformation. It's very simple. And we are going to show that with high probability, such a linear transformation works. I mean, this is not a linear transformation. This is kind of a way of sampling a linear transformation because, well, once you I just said that every entry is a random variable. A matrix of random variables is not a linear transformation. Once you sample a value for each entry of this matrix, then you get a matrix with real numbers as entries. And now you have an actual matrix, which is a linear transformation. So to actually construct a linear transformation, we will have to sample each entry independently, and then we will come up with a matrix of real numbers. And what we are going to prove is that with high probability, such a matrix is going to satisfy all the properties we need. So it's going to preserve all distances between all pairs of points in our data set approximately. Okay. And I claim it suffices to prove the following statement, that for a fixed pair of points in our data set, so just for a fixed u and a fixed v, the probability that the distances after the linear transformation and before the linear transformation do not differ by more than a factor of 1 plus or minus epsilon is at most 2 over n cubed. Okay. Two questions. What is the probability over, and why is this sufficient? You can answer either one of them if you want. You don't have to answer both at the same time.
It's probability over the draw of Gaussians in the matrix.
Right. So the probability is over the choice of G, or equivalently over the choice of phi. Okay.
Yeah, and I think this is sufficient to prove, because I think you'll be using Chernoff-Hofting in some way, and so you will get k, which is in logarithmic of n. And if
you are going one step ahead of me. You are telling me how I will prove this. I'm saying if I prove this, I'm done. Is that true? That's all I'm asking right now. Forget about how we prove this. Yeah, we'll get to that in a minute. But I'm just asking you, or I'm just claiming right now that, I mean, the statement I claimed on the previous page was different, that for all points u and v in the data set, distances are preserved. Here I'm saying I'm just going to prove it for a fixed u and v in the data set, but I'm going to prove this statement for an arbitrary pair u and v in the data set. Why am I done? The answer is 2 words. Okay. Starts with a u, ends with an e unbound. So
union bound.
Right. So the probability over the choice of G that there exists u and v in the data set such that, oh, I see. Maybe I wrote the wrong expression. This probability is extremely high. This is the good event. So this probability is extremely high. And what we want to say is that for all uv, we have the same thing. Okay, sorry, my bad. One minus the number of choices for the pairs u and v times the probability of a bad event for a fixed u and v, which is, and so this will be greater than or equal to 1 minus 1 over n, which is great because I will be able to claim that with probability at least 1 minus 1 over n, which is still sort of extremely good. In fact, it's tending to 1. A random G is going to simultaneously be a good choice for all pairs u and v. And I just wanted to show that a good linear transformation exists. Here I'm in fact proving that a random linear transformation is a good linear transformation with probability tending to 1. So it's certainly, I am proving that something like this exists. In fact, I'm proving that almost all linear transformations have this property when I pick them appropriately.
It's a probabilistic event, right? It's not exactly Johnson's Lindenstrauss.
I'm sorry?
It's not exactly Johnson-Lindenstrauss because that says there exists a linear transformation that guarantees your projections lie inside the ball.
But yeah, but I am proving that, right? I'm saying that the probability is over G, or the probability is over the choice of this linear transformation. So the inside stuff is dependent only on G. Right? So let's just call this as phi is good. Right? Let's call phi as a good linear transformation. Okay. And what Johnson-Lindenstrauss is claiming, there exists a good linear transformation. And what I'm proving here is that a random linear transformation is good with probability 1 minus 1 over n, over the choice of the linear transformation, not over the choice of points. There is no probability over the choice of points in the data set. There is an for all quantifier on the points. So Johnson-Lindenstrauss claims some good linear transformation exists. And I'm claiming, and I'm saying that a random linear transformation is good.
Yeah, but good with some probability. It's not exactly the same statement. That's what I'm thinking.
It's
good a probabilistic
with
version of Johnson-Lindenstrauss then.
No, it's just, well, it is a probabilistic statement, but it's actually stronger than Johnson-Lindenstrauss, not weaker. Because, I mean, think of the analogous statement, let's say, for independent sets. So suppose I make a statement that the graph has at least one large independent set. And then I end up proving that a random independent set is large with probability 2/3. That means there exists at least one large independent set, because if you just picked a random one with probability 2/3, you would end up with a large independent set. It's not an explicit independent set, so I'm not telling you how to find it. And so, so Johnson-Lindenstrauss, the way I stated it, I'm not saying that there is a kind of explicit algorithm to construct it. I just said that there exists one. And I'm saying, in fact, if you just chose things at random, you will find one with extremely high probability. The one you find will be good for all points. There is no probability once you find a good one. So, and you can check it. So just draw a matrix at random, and then you can, in polynomial time, just go over all points and check that this is a good linear transformation. And then you would have found one. Once you find a good linear transformation, there is no probability anymore. It's just good for all pairs of points. It's just that I'm not saying that. There exists is just a statement that even the probability is positive is stronger than the statement of there exists. And in fact, I'm proving that the probability is tending to 1.
So we had a condition for k to be less than equal to some logarithmic of n. Will that still apply?
So that will still apply. Yeah. So I will only be able to prove the statement for k, which is equal to the same kind of bound that I had, well, ln n divided by some function of epsilon. Okay, so for k equal to this, I will be able, this will be true for k greater than equal to this. I want k as small as possible. So in particular, for k equal to this number, I will be able to prove the bound on that I want on the probability. And so there will be a linear transformation with that particular choice of k. Does that answer your question?
Yeah.
Okay. Let's continue. So Now I've kind of narrowed down my goal to arguing about one fixed pair of points u and v, okay? Arbitrary, but fixed for the rest of the argument. And now let's kind of modify the statement a little further so that becomes a little cleaner to work with. So let's just recall what our definition of the linear transformation phi was. This was just G divided by root k, the matrix G with every entry divided by root k. And so phi of u minus phi of v is nothing but G times u minus G times v divided by root k. And so the norm square is just the norm of G times u minus v, norm square divided by k. And now let's write this condition a little differently. So let's move k to the extremes of the inequality, and let's bring the norm of u minus v square in the middle. And let's in fact take u minus v squared inside. So let's say we define w to be u minus v divided by the norm of u minus v. So in particular, w is a unit vector. Okay. It's a fixed but arbitrary unit vector. And so then we are trying to look at a statement which is of the form 1 minus epsilon times k is less than equal to the norm of g times w. Okay. And all these probabilities are talking about the same event. They're just writing it slightly differently in maybe with increasingly simpler expressions. Is it okay that these are all the same event for this particular choice of w? Okay. I'll take that as a yes, but stop me otherwise. Okay, so now let's study this last line, which is the probability that g times w, the norm of it, is between 1 minus epsilon times k or 1 plus epsilon times k. And then we want to prove that for a unit vector w, the unit vector is actually obtained in this way, but we'll prove it for an arbitrary unit vector. We'll forget about how we got to w. The probability that this event does not happen is really small. So the probability that what's written here does happen is extremely large. Okay. So let's get to a study of g times w for a unit vector w. So again, w is an arbitrary unit vector in R to the d, which was obtained by looking at u minus v divided by norm of u minus v, but we forget about that for now. It's an arbitrary unit vector which is fixed for the rest of the argument. And we are looking at g times w. W is in d dimensions, g has k rows and d columns, so g times w is in k dimensions. And we are studying probabilities over the choice of the entries in G. So every entry of G is a random variable. So every entry of this vector G times W is also a random variable. In fact, it's a random variable which is obtained in exactly this fashion. The first row is just W1 times the entry G11, W2 times the entry G12, and so on. And similarly, the ith row is a linear combination of entries of G in the ith row. Is that okay? So every entry of the vector G times W is a random variable. It's actually obtained by a linear combination of random variables which appear as entries of G. Okay. Because W is fixed and the entries of W provide the coefficients for this linear combination. Okay. Any suggestions, or can someone tell me what this random variable corresponding to a single entry, the ith entry in this vector looks like?
Normal with zero mean, norm of W Gaussian.
Right. So
Variance.
each of these entries is a standard Gaussian, and they are independent. And we just saw that linear combination of Gaussian random variables, of independent Gaussian random variables, is also a Gaussian random variable. And because it's just a linear combination, the mean remains the same, and the variance is the sum of the coefficient squared, which is just 1. So this is also a standard Gaussian random variable. And this is convenient, and in fact, it's a very useful property of Gaussians, this kind of linear combination. And we can start with some crazy linear combinations, but then just once it becomes a Gaussian, we can forget about how we got to this linear combination and just study a Gaussian variable. So let's call this xi, which is the ith entry of the vector G times W. And now let's look at the norm of this vector G times W, which is the quantity we are really interested in studying. This is the sum of squares of all the entries in this. There are k of them. And from what we just saw, x1 to xk are also standard Gaussians. And this takes maybe a moment's thought, but they're also independent. Because x1 only depends on entries in the first row of G. X2 only depends on entries in the second row of G, and so on. And all rows of G are independent of each other. So x1, x2, all the way up to xk are independent random variables. They are all random variables with Gaussian distribution with mean 0, variance 1. So now we have arrived at a relatively clean problem. We have Z, which is a sum of squares of k Gaussian random variables. Each of them just has mean 0, variance 1. All of them are independent. And we are asking, what is the chance that this we want to prove that there is a high chance that this random variable is between 1 minus epsilon times k and 1 plus epsilon times k. Okay. Or equivalently, we are asking what is the probability that this does not happen. So we want to show that the probability that Z is too large is small. And similarly, the probability that Z is too small is also small. Okay. So we will actually study each of these probabilities separately, the probability that Z is too large or too small. And now it sort of makes sense why this K appears. Expectation of Z is just the summation of expectations of xi squared, which is just each of these terms is 1, so the sum is K. So expectation of Z is K, and we're just asking the question, what is the chance that Z is bigger than 1 plus epsilon times its expectation or smaller than 1 minus epsilon times its expectation? Okay. Which is a question we have studied before in Chernoff-Hafting kind of bounds. And so there was already guessed earlier that we'll probably get this log by Chernoff-Hafting kind of calculations. And this is sort of writing the question explicitly in that form. Any questions before we continue? Okay. So to recap, we have Z, which is the sum of squares of independent Gaussian random variables. We just saw that the expectation of Z is K. And let's say we are asking the question, what's the chance that Z is too large? More than 1 plus epsilon times its expectation, or more than 1 plus epsilon times K. Okay. We've sort of, as I emphasized when we were doing Chernoff-Hafting, that the proof technique is fairly general and is useful in many situations. And this is just one more example. So we'll actually use the fact that here we can write the probability as the probability that e to the lambda Z is greater than equal to e to the lambda times 1 plus epsilon times K for any positive choice of lambda. And we'll choose lambda in a bit, but we can analyze this event for any positive lambda that we're interested in. And then apply Markov's inequality. So Markov's inequality tells us that this is less than equal to expectation of e to the lambda Z divided by whatever appears on the right hand side, which is e to the lambda times 1 plus epsilon times K. Okay. And as in Chernoff-Hafting, if we can compute this expectation, we obtain the bound we want. And just as before, this is kind of easy to compute because of independence. So e to the lambda Z is a product of e to the lambda times xi square. And because these are independent, we can write this expectation as a product of expectations. And it just so happens that we computed exactly this expectation in the previous lecture. So we already know what the numerator should be. It's for each individual xi, it's just 1 over square root of 1 minus 2 lambda, as long as lambda is less than half. But we are going to choose lambda. It's just that we are doing the computation for an arbitrary positive lambda to be determined later. So we will choose lambda, which is between 0 and half. Okay? So we'll be careful when we finally plug in a choice of lambda. Okay. But then we know how to calculate this. It's just 1 over square root of 1 minus 2 lambda for each of these xi's. So there are k of them. So this is a bound on the probability that we are stuck. Any questions before we continue? An important part is that this is exponential in k. this probability, and we'll kind of simplify a little bit so that the stuff is maybe less than 1, the ratio, and then it's exponential in k. So choosing k to be roughly some constant times log n will suffice to make this probability smaller than a polynomial in 1 over n. And in particular, we chose some maybe 2 over n cube or 1 over n cube or something like that. So a choice which is roughly logarithmic in n will suffice. And then let's try to make that precise. So just to recap, we calculated the probability using Markov's inequality, and just simplifying it a little bit, or moving things around and taking the square root outside. So we get it's a ratio of some quantity which depends on epsilon and lambda, the whole thing raised to the k over 2. And we'll choose k later, and our goal is to try and simplify the stuff inside the bracket. A choice of lambda that turns out to be convenient for the bounds I want is epsilon over 2 times 1 plus epsilon. I mean, nothing too special about this choice. You can try to minimize this quantity and try to find other bounds. This is just convenient for the expression that I mentioned earlier. It's just relatively clean expressions that come out of this. But yeah, you can sort of optimize in whatever way you want from this point on. This point, all we are doing is computation. So plugging in this value of lambda, the bound simplifies a bit. So we have e to the minus epsilon in the numerator, and the denominator becomes, I guess, 1 over 1 plus epsilon. So we get 1 plus epsilon again comes up to the k over 2. And can simplify a little bit further. So using the Taylor expansion of e to the minus epsilon, we can say that this is less than equal to 1 minus epsilon plus epsilon squared by 2 times 1 plus epsilon to the k over 2. Again, simplify that a little bit more. We get 1 minus epsilon square plus epsilon square divided by 2 minus epsilon cube divided by 2 equal to the, plus k over 2. And so you get 1 minus epsilon square over 2 plus epsilon cube over 2. And again, using the fact that 1 plus x is less than equal to e to the x, you get that this is less than equal to e to the minus epsilon squared minus epsilon cube over 2. So here we used 1 plus x is less than equal to e to the x. Okay. Any questions so far? I mean, this is just a couple of inequalities. Once we get the only conceptual part is the application of Markov and use of independence. Okay, so this is bound on a one-sided deviation, and I'll leave it as an exercise to show that the probability that z is too small can also be bound similarly. And so combining the two, we get that the probability that Z deviates too much from its expectation in either direction by more than epsilon times k is upper bounded, or is bounded by 2 times what we obtained on the previous page. And now, you can see that this is less than equal to 2 over n cubed for k, which is sufficiently large. So if k is larger than whatever we had earlier, 12 ln n divided by, then the probability is less than equal to 2 over n cubed. And based on what we said earlier, is that the probability that there is any pair of points for which the distance deviates too much is upper bounded because of the union bound by n choose 2 times 2 over n cubed, which is less than equal to 1. So the probability over the choice of G, or equivalently the linear transformation phi, that there is any pair of points in our data set which for which the distances are not preserved, is at most 1 over n. So with probability at least 1 minus 1 over n over the choice of G, G is such that distances are preserved for all pairs of points. And so this is a good G. And we found it with probability approaching 1. So just picking a random one will be good enough to show that it exists. Any questions before we continue?
Why couldn't we use Chernoff-Hofting from the beginning?
Why couldn't we use Chernoff-Hofting?
Was it because xi squared were not 0, 1?
Yeah, so Chernoff-Hofting was proved, or at least the analysis we did was for sums of independent Bernoulli random variables, and in particular, for there we used the fact that the expectation of each one of these random variables when they were 0 or 1, we computed it by saying with probability pi, you get e to the lambda, and with probability 1 minus pi, you get 1. And that step doesn't quite work when we have Gaussian random variables. And it was not clear how to arrange things in a way, or construct G in such a way that for an arbitrary W, a single row of G times W is a Bernoulli random variable. That's pretty tricky. Entries of G could be Bernoulli, but then we have to look at G times W, or these strange linear combinations. And ending up with Bernoulli random variables there for an arbitrary W, I don't know how to do that. But for Gaussians, it's kind of nice. It's very easy to know how to end up with a Gaussian random variable after a linear combination if we start with Gaussian random variables before the linear combination. So it's more or less the same proof. It's just that we chose a random variable which behaved nicely under linear combinations. Does that answer your question?
Yeah.
Okay. Any other questions? I should say that it's not that Gaussians are sort of the only random variables with which you can do this. This sort of phenomenon happens for many different choice of random variables as entries of our matrix. And I'll say a little bit more about that. It's just that the proof requires a little more work. So it's not that the theorem is false for other kinds of random variables. There are lots and lots of different choices for which similar statements hold. It's just that the proof you need to be a little more careful. Okay. And with Gaussians, because of this very clean linear combination property, it's a very simple proof. Okay. So it's more the convenience of the proof rather than the truth of the phenomenon that motivated the choice of Gaussians for me. Okay. It should mention, I mean, we'll not prove this, but we got log n from this kind of union bound, and we said that well, we have this unit vector w, which comes from a pair of points u and v, and so because there were n points in our data set, there were basically n squared choices for this vector w, and there are kind of more interesting statements which get a bound which is possibly better than log the number of w's than we can have. In particular, there are statements which work even for possibly infinite subsets of R to the D, where these subsets are really subsets of vectors. So I'm writing the sphere in a really complicated way, but this is just a T-1 dimensional sphere. So, and what we really proved in the previous argument is that if you have a set T, then for any single vector, the probability is kind of exponentially small in K. And so if you have K larger than log of the size of T, then you can always take a union bound and you will have it simultaneously for all vectors in this set T. Okay. Log of the size of the set is the kind of simplest union bound that we can take. But if you know more about this set of vectors that you're talking about, you can get much better bounds. And in particular, you can get bounds if you know other properties of this set, or something which is called the Gaussian complexity or the Gaussian width of this set. And you can obtain bounds in terms of this rather than the size of the set, or log of the size of the set. And there are infinite sets for which you can still obtain very interesting bounds on the Gaussian width, which are finite and sort of simple functions of the dimension. And this sort of thing extends to many settings where we are taking union bounds. So there is a homework problem where we are talking about a class of hypotheses and you're trying to learn it from samples from a distribution. And we said you have kind of similar to this, there is a log of the size of the hypothesis set that appears. And it's a really interesting question of when can you do better than log of the size of the hypothesis set? And for example, if you know more about it, there are measures of how complicated is the set of hypotheses. And one such thing is what's called the VC dimension of the set. And if you can say that in some way, I know that this set of objects over which I'm taking union bound is kind of simple, then you can do better than the naive union bound. And this appears as Gaussian width, also something called Rademacher complexity. This appears as VC dimension in kind of hypotheses. So, and these are all related. So it's a just wanted to mention that there are statements which can work possibly with infinite sets, or which can do much better than log of the size of the set. And a highly recommended source for reading much more about this kind of analysis is the textbook on high dimensional probability by Verschunden, which is also linked from the course webpage. Yeah, sort of has lots of interesting results and tools for probabilistic analyses. We've only been able to cover some very small fraction of things in this course, but do look it up if you're interested. Okay. I should also say that, as I was kind of saying before, there are many interesting generalizations of how you can choose this random matrix. You can choose entries to be independent plus minus one variables, which are easier to sample from rather than Gaussians. I mean, if you can generate random bits, each random bit is already giving you a plus or minus one entry. Probably takes a little more work to see how you, if you can have random coin tosses, how do you generate Gaussians from them? There's also a whole theory of how to work with sparse matrices when you're doing this linear transformation. So the matrix G we constructed, every entry is likely non-zero. So it maybe has very few zero entries or maybe no zero entries. On the other hand, if you had lots of zeros, it would be really convenient to multiply a vector u with this matrix. And so there is a lot of advantage to being able to work with sparse matrices. And again, there is a whole theory, and there are many interesting results in this direction. And you can do the same kind of arguments, or you can prove the same kind of phenomena working with sparse matrices, or the proof requires more work. And you can also work with, instead of ±1, or you can in general work with what are called sub-Gaussian random variables. And in some sense, this expectation that we computed, which is e to the lambda x squared, this is really one of the definitions of how Gaussian-like some random variable is. So in a slightly different language, if expectation of e to the x squared divided by k square is bounded, and again, doesn't matter what we bounded by, but let's say 1 or 2 or whatever you want, then we will kind of use this parameter k as a measure of how good a random variable x is. And this is called the Subgaussian norm, or the Orlick's norm of this random variable. And in general, sort of any generic random variable for which this some reasonable small k works is called a Subgaussian random variable. And these are sort of a significant generalization of what you can do with Gaussians. In many cases, it's possible to do what you're doing with Gaussian random variables with Subgaussians. We don't always know proofs of these in all kinds of settings, but it's a good proxy in many different applications. And for whatever reason, you might be interested in working with this more general class. And so, yeah, it's really the integral is computed with, fairly simply for Gaussians. It generalizes, and it's used to define a class of random variables. Finally, let's get back to some discussion on the two methods of dimension reduction that we saw so far. One is Johnson-Lindenstrauss. So you start with a bunch of points, and we sampled this random matrix G, and then computed some linear transformation of all points, and we declared that with high probability we'll be able to find a good linear transformation such that all distances are preserved. So this low dimensional proxy for our data set is a good one. All distances are approximately preserved. We also did something to reduce dimension using singular value decomposition. We said if you are given a bunch of points, these are in d-dimensional space, then you can find a k-dimensional space such that the sum of square distances of these points to this space is minimized. And so in particular, if you project all points to this space, you get points in k-dimensional space. And that's in some sense a good low-dimensional version of our data set. Any thoughts on how these two processes compare, when to use one or the other, or what might be similarities or differences in these? First, do you agree that these are both methods of dimension reduction? Yeah. Now we are done with the formal proofs part of the lecture, so we are just at this point discussing or speculating or hypothesizing, whatever you want. Any thoughts?
I think if compute is important, like you don't have a lot of compute, and you are okay with like approximate projections, then Johnson-Lindenstrauss is better than SVD, because SVD you have to compute the components, or you don't have to compute the components, but you have to compute the projections, which is order n cube, I think, d cube.
Right. So you need to compute this. I mean, again, there are ways of computing SVD faster, so you don't really need to compute. I mean, there's also a nice book by Santosh Vampala called The Random Projection Method, which in particular gives you algorithms for fast SVD. And also it's a nice book to look at if you want to see some examples of this. But you can do some random projections and then compute the singular value decomposition to get an idea of singular values. You don't really need to do the full computation. But yes, there is some computation involved in finding the eigenvectors or singular vectors, etc. All of that can be done to some extent in a fast, approximate way. But Johnson-Lindenstrauss, I agree with you in some sense that it's intuitively, at least in terms of description, it's very simple. Just sample a matrix with random entries. Particularly if you could sample a random matrix, that would make our life even easier. A random matrix, or sorry, random sparse matrix, that would make our life even easier. One interesting and important difference is the dimension reduction in Johnson-Lindenstrauss is linear. We just chose a matrix G, and the new data set we got was just obtained by a linear transformation of the old data set. That's not necessarily true for SVD. I mean, we are doing a projection to this subspace, but the subspace also depends on the data. So the projection operator that we are applying is also dependent on the point sets, on the points U1, U2, and so on. And so this is a nonlinear method. So in particular, if you want to understand what happens to U1 plus U2, it's very easy to understand it in the first case, not necessarily in the second case.
Can we say something about differences being preserved in SVD? So in
right,
Johnson,
yeah, good point. So we don't quite get the differences being preserved. What we got there was some sort of average statement that maybe it's the best low rank approximation if we, or like for a matrix, if we are trying to look at some kind of norm of the new matrix and the old matrix, which is dependent on some notion of sum of distances or some function, some global function of these distances. By choosing different functions, you can get some bounds on maybe most distances if you choose some sort of a strong enough function, but the guarantee that you would get in the first place will always be some form of sum of distances or some sort of global average over points, and not really an individual one. Although, yeah, you can massage statements to obtain those kind of guarantees. Right, and again, maybe the Blum, Hopcroft, and Kannan book, Foundations of Data Science, has some statements or some sort of interesting consequences of what you can get out of SVD. So take a look at there for some interesting corollaries of the guarantees you get from SVD. Another difference is that, as stated, SVD is often applied when your data set is really low dimensional and you can get something out of it even with 2 or 3 singular vectors or some very small number of eigenvectors. Whereas Johnson-Lindenstrauss is something where is applied when we are really trying to get a guarantee without looking too closely at the data, just saying that some sort of random matrix or random map is going to be useful. So when we are interested in sort of using some properties of the data more closely, SVD is kind of a nice choice. When we are trying to argue without having to, for whatever proof we are interested in, we may want to prove it in more generality, or it gets too complicated to look at the data. Then this sort of oblivious proof that Johnson-Lindenstrauss has without really thinking about what the points you want to UN look like is more advantageous. So these are just some observations. And of course, these are not the only methods for dimension reduction. There are many more. These are just a couple of examples that we saw through the sort of concepts we studied in the course. All right, with that, let's end the lecture and end the course. The exam is next week. Refer to my announcements from the previous lectures for all details, also on Canvas. And I'll stay on for a few minutes after the lecture. I'll also have office hours next week. Let me know if you have any questions.